Fantastic. And could you please put that into the perspective of what's going at the top of the stack? Because that's where we want to develop applications and algorithms that will move us towards the true NISQ era.
Yeah. In terms of I think it's, we've heard over the last period as quantum computing it's come off the top of its initial wave of it's come off of peak hype. We know a lot about the challenges it faces, whether that's the pessimism over what can be achieved with variational quantum algorithms, whether that's the realization that only a quadratic speed up is not enough for the architectures that we're working with at the moment, whether it's skepticism about, even in quantum chemistry, which we think is a great application area, is it really right to speak about an exponential advantage? And people have hit back in all of these areas. So there's been a lot of challenging press out there. But I think we also have to remember some of the real strengths that still make quantum computing a radical transformative technology, are still set to make quantum computing a radical transformative technology. Of course, there's cryptanalysis. When we get to a large enough machine to run Shor's algorithm, that is a big deal for people that want to do that. And there are a lot of governments and government agencies that in essence want to do that. And I also think, though the excitement at the beginning of the year, or disquiet perhaps I should say at the beginning of the year, about Schnorr's algorithm and variational approaches run by a Chinese group, that probably doesn't work, but I certainly would not dismiss the notion that a hybrid heuristic cryptanalysis approach could get over the line before we get to running full-scale Shor's algorithm, and I think people have to keep that in mind. I also think that though it's right that we should not overstate what we know about how we can tackle quantum chemistry problems, I think there's a lot of building evidence that Feynman's dream that we can really use quantum to simulate quantum remains very much on track. The great progress we saw from, for example, Continuum and others, of demonstrating non-abelian topological order on their devices was fascinating basic science and physics. And it's not the only example. We've used these early quantum devices, even these quantum devices that are not really beyond classical simulation yet. We've used them to do very interesting analysis of physical systems. And that's not just interesting for physicists, it's an indication that we really are on the right track of believing that these devices will be a fundamental enabler for us doing better quantum science, whether that's in materials, whether that's in chemistry, as we progress. Heuristic optimization, it's difficult to pin down. Often we don't really think that there's a specific quantum advantage yet. It's something that we can also tackle by quantum-inspired methods. But that in itself is a great business opportunity for businesses that find themselves doing something better and more efficiently than they previously had. I think there's continuing interesting developments here. Obviously, a lot of conventional hardware innovation coming out of Japan, but also interesting software innovation. A recent one that sticks in front of my mind is Multiverse's introduction of a new tensor network tool, which is quantum inspired with potentially very interesting applications. I also, at the slightly more abstract level, developments like Lin and Tong's approach to make quantum phase estimation more efficient, or the remarkable Yamakawa-Zand reconstruction, which gives us a whole new way of thinking about how we can get quantum advantage without there being structure in the problem. It illustrates how alive the whole algorithmic area remains.